The universe is everything: space, time, matter, energy, and even you. Earth, the moon, planets, stars, and galaxies are all part of this cosmic dance. Our sun is one of billions of stars in the Milky Way, and the Milky Way is just one of billions of galaxies, each hiding a supermassive black hole at its heart. Everything we see and can't see is part of the universe. Space isn't far. It's just 62 miles above your head, and Earth is floating in it. Earth may feel safe, but it's a fragile bubble in the hostile cosmos. Without studying space, we'd be in the dark about our own planet, its orbit, its quirks, or why it teems with life while others are barren. Understanding our cosmic origins is like finding our place in a giant puzzle. But if the universe seems like a riddle, don't worry. This video breaks it down, piece by piece, so you won't need to look elsewhere for the basics. Stick around till the end, and you'll walk away feeling like a universe expert, armed with the foundation to explore even deeper mysteries. So, how old is the universe? Well, let's dive in and explore this fascinating question together. The universe is everything, every bit of energy and matter. Most of what we see is hydrogen, the simplest atom, just a proton and an electron. When you clump atoms together, you get molecules. Gather trillions, and you've got a dust particle. Mash a few tons of elements like carbon and oxygen, and you've got an asteroid. Collect 333,000 Earth masses of hydrogen and helium, and you've got a sun-like star. Humans categorize these collections: planets, stars, galaxies, and even raccoons. They're all different, but follow the same laws of nature. Our Milky Way alone contains 100 billion stars, and the observable universe holds at least 100 billion galaxies. But all that visible matter, it's less than 5% of the universe. The rest? A mystery. 27% is dark matter. 68% is dark energy, which we can't observe but know they exist. Scientists figured that the universe is 13.8 billion years old. They found that by measuring ancient stars and the expanding universe, everything used to be closer, hotter, and packed in one spot until the Big Bang. Time, space, and everything began there. The term Big Bang was coined in the 1940s by Fred Hoyle. The theory explains how the universe started from a single, infinitely hot, dense point that expanded over 13.8 billion years into the vast cosmos we see today. Though we can't directly witness the Big Bang, evidence like the cosmic microwave background, CMB, which is the leftover radiation from the Big Bang or the time when the universe began. This expansion filled the universe with matter and radiation. In the first second, the temperature hit 10 billion degrees Fahrenheit, 5.5 billion Celsius. Fundamental particles, neutrons, protons, electrons were born. At first, this hot soup was too dense for light to escape, like sunlight trapped in clouds. About 380,000 years later, electrons combined with nuclei, forming neutral atoms, allowing light to shine through. This light, now known as the CMB, was first predicted in 1948 and accidentally discovered in 1965 by Arno Penzias and Robert Wilson, who initially thought pigeons nesting in their equipment caused interference. Before the Big Bang, it is thought that all four fundamental forces were unified. As the universe rapidly expanded and cooled following the Big Bang, the fundamental forces separated from each other in a process called symmetry breaking. And as a result, we had gravity, electromagnetism, weak nuclear force, and strong nuclear force. The early universe was a scorching cauldron, a cosmic kitchen where the first elements were cooked up in a primordial dance of physics and chemistry. This process, known as nucleosynthesis, set the stage for everything that exists today. In this nascent universe, only two fundamental particles were at play: protons and neutrons. Think of them as the red and white marbles of cosmic creation. These were the only ingredients available, and Mother Nature had just 3 minutes to work with them before the universe expanded and cooled too much for further synthesis. In those fleeting moments, Mother Nature, the universe's unseen architect, crafted the simplest elements: Hydrogen, the most abundant element, was the easiest to make. A single proton, one red marble. Next came helium, requiring a quick combination of 2 protons and 2 neutrons. 2 red marbles with 2 whites. Helium formed almost as abundantly as hydrogen. Lithium, a rare recipe, needed 3 protons and 3 or 4 neutrons, making it a trickier combination and explaining its scarcity in the universe today. Why not heavier elements? The rapid expansion and cooling of the universe acted like a constantly shifting kitchen floor, too unstable to assemble more complex structures. The laws of physics placed an insurmountable barrier on combining these simple particles into anything larger within that early time window. Moreover, combinations that involved 5 or 8 particles lacked the stability needed to hold together. The universe's elemental pantry was stocked with only hydrogen, helium, and a sprinkle of lithium. As the universe continued to expand and cool, a critical transition known as recombination occurred. Before recombination, the universe was a dense, hot soup where light couldn't travel freely. It constantly collided with charged particles, much like navigating through a foggy crowd. But as things cooled, protons and electrons, previously frenetic and unattached, began to pair up, forming neutral atoms. This process, called recombination, turned the universe transparent. Light could finally travel long distances without interference, like a path clearing in a dense forest. The universe's first snapshot, the cosmic microwave background, or CMB. This newfound transparency allowed the first light to travel unobstructed, creating what we now observe as the cosmic microwave background. This is the universe's first portrait, a snapshot of its state roughly 380,000 years after the Big Bang. The CMB reveals a remarkably uniform universe. The early universe was like a vast, cold room filled with thin air. Over time, some corners of this room began to collect more gas, like clumps forming in a thickening soup. Gravity, that invisible force pulling everything together, started to act like a magnet on these denser spots. The more gas that gathered, the stronger the gravitational pull became, sucking in even more. As gas kept piling up, the centers of these dense regions heated up. Think of it like rubbing your hands together faster and faster until they burn with friction. Eventually, things got so hot and crowded that nuclear fusion ignited, a cosmic spark setting everything ablaze. This fusion is what makes stars shine. Hydrogen atoms fusing into helium and releasing vast amounts of energy. And with this fiery birth, the first stars flickered to life. These first stars, known as population 3 stars, were beasts, hundreds of times larger than our sun. They were like the floodlights in a pitch-black stadium, suddenly lighting up the vastness of the universe. But they weren't just lights. They were also the universe's first factories, producing heavy elements like carbon, oxygen, and iron. When these massive stars ran out of fuel, they exploded in supernova, scattering these freshly minted elements across the cosmos. Like a chef tossing ingredients into a salad, these elements would go on to form planets, moons, and eventually, life itself. When these first stars flicked on, they did more than just light up the darkness. They kick-started a cosmic cleanup operation known as reionization. Before this, the universe was filled with a thick haze of neutral hydrogen, blocking light like fog on a dark highway. The intense ultraviolet radiation from these new stars was like the rising sun burning away morning mist. The hydrogen fog got torn apart, ionized, into protons and electrons. Slowly, the universe became transparent, like a window clearing up after a heavy rain. But this process didn't happen overnight. It took hundreds of millions of years for enough stars to form and burn away the fog. Slowly, patches of the universe opened up to the light, revealing a new, clearer cosmos. Just as a blacksmith transforms raw iron into intricate tools and structures, stars transmute simple elements into more complex ones through the intense heat and pressure at their cores. The process begins with the most abundant and simplest element in the universe, hydrogen. Like kindling for a fire, hydrogen fuels the initial stages of a star's life. Deep within the stellar core, temperatures soar to millions of degrees, creating conditions where hydrogen atoms can overcome their natural repulsion and fuse together. This fusion is akin to fitting puzzle pieces together, with 4 hydrogen nuclei combining to form a single helium nucleus. As this cosmic puzzle solving continues, the star releases an enormous amount of energy, the very light and heat that allows life to flourish on planets like Earth. It's as if each successfully completed puzzle radiates a burst of power, illuminating the vast darkness of space. But the story doesn't end with helium. As stars age, they become even more proficient at their craft. Like an artisan mastering increasingly complex techniques, stars begin to fuse helium into heavier elements. Carbon, oxygen, and nitrogen emerge from this process, the very elements that form the basis of life as we know it. It's as if the stars are unknowingly preparing a cosmic recipe, mixing the ingredients that will eventually give rise to planets, organisms, and even conscious beings capable of pondering their own origins. For stars up to about 8 times the mass of our Sun, this is where the forging process ends. These stars lack the extreme conditions needed to create elements heavier than iron. However, for more massive stars, the cosmic forge reaches temperatures hot enough to produce elements all the way up to iron. Imagine these massive stars as industrial-scale factories, churning out a diverse array of elements at an astounding rate. In their cores, silicon fuses into sulfur, sulfur into argon, and so on, each step producing heavier and more complex elements. This process continues until iron is formed, the heaviest element that can be produced through fusion while still releasing energy. The production of iron marks a critical turning point in a star's life. Like a machine that has run out of fuel, the star can no longer sustain itself through fusion. What follows is one of the most spectacular events in the universe: a supernova explosion. A supernova is nature's grandest fireworks display, an explosion so bright it can outshine entire galaxies. But it's more than just a light show. In the fleeting moments of a supernova, conditions become so extreme that even heavier elements, gold, silver, uranium, and more, are forged. It's as if the dying star, in its final act, unleashes all its creative energy to produce its most valuable and complex creations. This explosive finale serves another crucial purpose. It scatters the newly forged elements far and wide across space. Like a farmer sowing seeds, the supernova spreads the ingredients for future stars, planets, and potentially life itself throughout the cosmos. The enrichment of the cosmos. Second and third generation stars. The aftermath of these stellar explosions marks the beginning of a new chapter in cosmic evolution. The interstellar medium, the vast, mostly empty space between stars, becomes enriched with these newly forged elements. It's like adding flavor to a bland soup. The once simple hydrogen and helium mixture now contains traces of heavier elements, setting the stage for the next generation of stars. When new stars form from this enriched material, they're fundamentally different from their predecessors. These second and third generation stars are like children born into a world full of resources their parents never had. They incorporate these heavier elements from birth, resulting in more complex internal structures and different life cycles. Our own sun is one such later generation star. It contains elements that could only have been created in previous generations of stars. In a poetic sense, we are made of stardust, the atoms in our bodies were once forged in the hearts of long-dead stars. These newer stars tend to have longer lifespans than their predecessors. It's as if the inclusion of heavier elements allows them to burn their fuel more efficiently, like a well-tuned engine compared to a primitive one. This longevity has profound implications for the potential development of life in their vicinity. Moreover, these stars are more likely to host planetary systems. The presence of heavier elements in the protoplanetary disks surrounding young stars provides the raw materials necessary for planet formation. It's like having a more diverse set of building blocks. With more options available, more complex structures can be built. The birth of planets and solar systems. As these enriched stars form, they're surrounded by swirling disks of gas and dust, the leftovers from their own birth. These disks are like cosmic construction sites where the materials for planets, moons, asteroids, and comets are gathered. Imagine this disk as a giant cosmic pizza with the star at its center. Over millions of years, bits of topping, dust grains, and ice particles start to stick together. It's a process not unlike how snowflakes form, growing larger as they collide with more particles. As these bodies grow, their gravity increases, allowing them to attract even more material. The largest bodies, called planetesimals, act like cosmic vacuum cleaners, sweeping up nearby matter and growing ever larger. It's a case of the rich getting richer. The larger a body becomes, the more efficiently it can accumulate more mass. In the inner regions of the disk, where temperatures are higher, only materials with high melting points can survive. This is where rocky planets, like Earth, form. It's as if the heat from the star acts as a refining furnace, leaving only the most resilient materials behind. Further out, where temperatures are cooler, ice can survive. This allows for the formation of gas giants like Jupiter and Saturn. These planets start as rocky cores but are massive enough to hold on to large amounts of hydrogen and helium, like cosmic lint rollers picking up the leftover gas in the disk. The formation of a planetary system is a delicate balance. Too close to the star, and planets may be too hot to retain their atmospheres. Too far, and they might not receive enough energy to support potential life. It's like finding the perfect spot in a room. Not too close to the fireplace to get burned, but not so far that you can't feel its warmth. Our solar system, with its diverse array of planets, moons, asteroids, and comets, is a testament to the complexity that can arise from this process. Each body tells a part of the story of our system's formation, like pages in a cosmic history book. The first galaxies, cosmic cities. As stars gathered, gravity pulled them closer and closer together. Stars clumped to form the first galaxies, like raindrops merging to create streams. Galaxies are the cities of the universe, bustling with stars, planets, and cosmic activity. In these early times, galaxies were more like small towns, clumsy and chaotic. The universe was still rough and tumble, with proto-galaxies crashing and merging in cosmic pileups. Each collision wasn't just a fender bender. It was a star-studded spectacle, galaxies mixing and mingling like two cities colliding and combining their neighborhoods. These galactic smash-ups weren't just violent, they were creative. New stars formed from the debris, and galaxies grew larger and more organized over time. From these messy beginnings, more complex structures evolved. Galaxies didn't stay isolated. They began to form clusters, drawn together by gravity like people gathering in crowds at a festival. And these clusters, too, grouped into even larger superclusters, sprawling across vast distances. Imagine them as megacities in the universe, hubs of activity connected by a network of highways, the cosmic web. This web isn't just random. It's an enormous, interconnected structure made of long strands of galaxies, with vast, empty spaces in between. Think of it like a 3D spider web, but instead of silk, it's woven from galaxies and stars. The filaments, these glowing threads, are where galaxies gather, while the spaces between are nearly empty, like cosmic deserts. But here's the twist. When astronomers mapped out the universe's visible matter, all the stars, gas, and dust, they found there wasn't enough to explain the cosmic web's intricate structure. Enter dark matter, the universe's hidden scaffolding. Dark matter doesn't shine or reflect light. It's invisible, but it does have mass and, therefore, gravity. Think of it as the invisible threads holding up the visible universe, like the unseen strings supporting a puppet show. Dark matter clumps and stretches across the cosmos, amplifying tiny differences in density, much like how a magnet organizes iron filings. It helped guide ordinary matter, like stars and gas, into the dense filaments and nodes of the cosmic web, forming the galaxies and clusters we see today. This cosmic construction is still happening. Galaxies continue to drift along the filaments of the cosmic web, sometimes colliding and merging in spectacular displays. Clusters are still pulling in more galaxies and gas. Even our Milky Way is on a slow-motion collision course with its neighbor, Andromeda, set to merge in about 4 billion years. No need to worry, though. That's plenty of time away. Meanwhile, the universe itself is expanding. The cosmic web is stretching like a rubber band being pulled from all sides. The strands grow thinner and the spaces between them widen, creating an ever-evolving masterpiece. From the forging of elements in the hearts of stars to the intricate dance of organic molecules on planetary surfaces, the story of cosmic chemical evolution is one of increasing complexity and possibility. It's a testament to the creative power of natural processes, operating over vast spans of time and space. As we continue to explore our universe, we're constantly adding new chapters to this story. Each new discovery, whether it's a distant exoplanet, a complex molecule in an interstellar cloud, or a potential sign of life beyond Earth, helps us better understand our place in this grand cosmic narrative.